Hello and welcome to this video on heterocyclic chemistry. Here we'll be looking at selective synthesis of furans and pyrroles. To start off with, we're going to look at the binary furan synthesis. This is a synthesis in which we synthesize a furan starting from a 1,3-dicarbonyl species and an alpha chloroketone. So the 1,3-dicarbonyl species has an acidic proton because it's between two electron-driven carbonyls. So treatment with the base forms the corresponding enolate. Then, if we add in an electrophile such as alpha chloroketone, then we'll get attack of the enolate through the carbon onto that ketone. Then we can get protonation of the resulting O-, as well as that acidic proton which still sits between the two carbonyls, can come back through and cyclize through the oxygen, displacing the Cl- leaving group. This builds our 5-membered ring, and the last step is the loss of H2O from our system to give us the aromatic furan. So, more slowly. We start off with our 1,3-dicarbonyl species. And an alpha chloroketone. Under basic conditions, we could remove this acidic proton that sits between two electron withdrawing carbonyl groups. And this gives us the corresponding enolate. Now we can have attack of the enolate through the carbon onto that electrophilic carbonyl center. And that builds a new carbon-carbon bond. We still have an acidic hydrogen between those two carbonyl groups. So if we use the base to remove the proton, we can start a cyclization through the oxygen onto the carbon with the chloride leaving group. And we can also protonate that O- from water. This constructs the 5-membered portion of our heterocycle. And finally, we can regain aromaticity by losing water from the molecule. So if we look at our alpha haloketone, that contained two sites of electrophilicity. We had the ketone and the chloride. In this reaction, we saw it was the ketone which reacted first because that's a better electrophile than the chloride. However, we can change the order of events. If we take our alpha chloroketone and mix it with sodium iodide, then we'll get an equilibrium whereby the iodide displaces the chloride to make sodium chloride, which is insoluble in a solvent such as acetone, and also our alpha iodoketone. Now, because the iodine is now a better electrophile than the carbonyl, what we can see is the order of events has reversed. Now, first of all, we get the same thing again. We get deprotonation of the acidic proton between those two carbonyl groups, but this time we get attack through the carbon onto the carbon bearing iodine. Again, we still have an acidic proton between the two carbonyls, and this, as last time, promotes the cyclization to make our 5-membered ring. Finally, loss of water builds our aromatic system. So, starting with the same dicarbonyl species as last time, with that same acidic proton, we add a base, and that forms the corresponding enolate. Now we add our electrophile, but this time the iodine means that we're going to get attack at the iodine end rather than the carbon aisle. So we push the arrows back through the negative charge, remaking that carbon-oxygen double bond, and the carbon attacking to make a new carbon-carbon bond and leave iodide. Now we still have another high acidic hydrogen between the two carbonyls. So if we remove that, we can get attack through the oxygen onto the carbonyl, thus making our 5-membered ring. Protonates the resulting negative charge. And we can lose the oxygen lone pairs to kick out the leaving group. And finally, loss of that proton gives us our aromatic system. This time with the methyl group at the 2 position, whereas last time it was at the 3 position. Moving on and having a look at Pyrrole synthesis, again we find the 1,3-dicarbonyl is a useful building block. But this time, instead of an alpha halo species, we're going to have an alpha amino species. Now, an amine reacts very quickly with a carbonyl to form the corresponding enamine. So we get attack of the nucleophilic nitrogen onto the electrophilic carbonyl, and then loss of water and loss of a proton to give us that enamine. Now the enamine is electron rich, and then we also have an electron poor carbonyl, so we can push the arrows around the ring to form our 5-membered ring, making that carbon-carbon bond. And finally, loss of water gives us our aromatic Pyrrole product. So we start off dicarbonyl starting material, and we have our alpha amino ketone. In the formation of an enamine, we get the nucleophilic nitrogen attacking our electrophilic carbonyl. This carbonyl is very electrophilic because it has another carbonyl next to it, withdrawing the electron density and therefore enhancing the electrophilicity. So this constructs the first new carbon-nitrogen bond. And then to complete the enamine formation, we get formation of aminium by loss of water. And then we can lose a proton to give us the enamine. Our enamine is electron rich because of this lone pair on the nitrogen, and so we can push electron density through via the carbon to attack the carbonyl and make the carbon-carbon bond. We can neutralise this resulting positive charge from using that nitrogen lone pair. And then finally, the loss of water from our system gets the aromatic Pyrrole product. The problem with this is that our alpha amino carbonyl is a compound that does not exist for very long. It's a compound that contains a nucleophile in the form of the nitrogen, but also an electrophile in the form of the carbonyl. And therefore, if we have a lot of this species, it will dimerize, and when it dimerizes, it will no longer be useful to us. So if we want to use this kind of reagent in a reaction, then we need to find a surrogate. And one way to do that is to mask the lone pair, for example by the HCl salt, and then by doing the reaction under basic conditions, which will slowly release the NH2, or by making a corresponding oxime, so that's the double bond nitrogen, single bond oxygen, hydrogen, and then using zinc, a very mild reducing agent, to reduce it in situ. So, we've seen a few different syntheses of Furans and Pyrroles. We've seen the thiospinaric synthesis, which uses a 1,3-dicarbonyl species and an alpha halo carbonyl, and depending on whether that halogen is a chloride or iodide, we can tune the order of reactivity and select between two products. We've also seen a nor-pyrrole synthesis, again exposing a 1,3-dicarbonyl, but this time with an alpha amino carbonyl, and we've seen that this is important to consider where we get that reagent from. Thanks for watching, see you next time.